What's the difference between a strong acid and a weak acid? And how sure are you that you know the answer? I'm Tyler Farah, and this lesson is all about acid-base chemistry. This is a content area that is rife with misperceptions and confusing nomenclature. So you'll know you've got this nailed down when you can execute confidently the learning goals seen on screen. Take a moment and read through this question stem right now. In this prompt, we're presented with an apparent paradox. We're told that concentrated HCl, probably no surprise, it can cause immediate, often very severe chemical burns. But we're told that HCl probably is not going to kill you. You're going to be burned, but you're going to be okay in the long run. By contrast, HF is nasty stuff. A splash of this on your skin will soak into your skin, enter your circulatory system, where it can thereby attack your heart, your lungs, other major organs in your body. This stuff is so brutal that it can even penetrate down into your bones, so that even small splashes of this stuff can be fatal. And this is despite the fact that hydrofluoric acid is a quote-unquote weak acid. Therein lies the paradox. Basically, how is it that the so-called weak acid can be so much more dangerous, so much more potentially deadly than HCl, which is a strong acid? We're going to end up seeing that the resolution to this paradox has to do with the fact that when scientists classify an acid as strong or weak, they mean something very specific. And what they mean has almost nothing to do with whether or not an acid is relatively safe or relatively dangerous. With that idea in mind, let's take a look at some math. In this first prompt, we're asked to compare the K value, Ka, for HF versus HCl. Ka of HF is significantly less than 1. What does that tell you about the HF deprotonation reaction? Recall that equilibrium constants tell you the ratio of products over reactants at equilibrium. And the fact that HF's equilibrium constant is so much smaller than 1 tells you that the denominator must be dominating. This reaction heavily favors the reactants, at least initially. But what we're going to see is that if you splash some HF on your skin, a small amount of it will deprotonate, forming a small amount of this hydronium cation, and then that hydronium cation is slowly going to cause damage to your tissue. It's going to leach into your body. Think about what Le Chatelier's principle would have to say for this reaction. As we consume the product, as it attacks your body, what effect is that going to have on the overall equilibrium? As the hydronium cation on the right attacks your body, this equilibrium is going to continually shift over to the right in order to continually supply more hydronium cation. This actually explains why hydrofluoric acid can take several hours to have the damaging physiological effects described in the question stem. How about HCl? Here, the acid dissociation constant is many orders of magnitude greater than 1. What does that imply about the deprotonation reaction of hydrochloric acid? In this reaction, the very large K value tells us that HCl is going to react with water almost immediately, so that this reaction really drives over to the right-hand side. So if you came in contact with this solution, you would come into immediate contact with those damaging hydronium cations. This explains why HCl causes those immediate burns. However, keep in mind, at the same time, if you were exposed to HCl, you'd get hit with those hydronium cations right away, but there wouldn't be more coming down the pipeline. That's the difference between HF and HCl. This starts to give you some idea of the differences between strong acids and weak acids. In fact, a lot of times strong acids are loosely defined as acids that completely deprotonate in solution, whereas weak acids are acids that enter equilibrium. I want to take this idea a step further with you, though, and apply rigorous mathematical rules for what makes a strong acid versus a weak acid. Let's start by considering the hydronium cation itself. The hydronium cation is significant because it's literally the definition of acidity. pH of a solution is calculated directly from the hydronium cation concentration. I want you to consider when hydronium cation reacts with water, what will be the products of that reaction, and what would therefore be the equilibrium constant describing that reaction? In the reaction between the hydronium cation and water, water is going to grab one of the protons away from the hydronium cation, but of course that just turns the hydronium cation into water, and it turns water into a new hydronium cation. It's kind of like we're playing hot potato with protons. Well, if we look at the equilibrium constant here, we see that because the products and reactants are exactly the same, we're going to end up with the same thing on top and bottom, and this all reduces down to the number 1. All of a sudden, it starts to seem a lot more significant that HCl had an acid dissociation constant greater than 1, where hydrofluoric acid has an acid dissociation constant less than 1. A second really important reaction when it comes to acid-base chemistry is the autoionization of water reaction, which is shown in part on the right-hand side of your screen. Take a look at that reaction and determine what the products of water reacting with water would be, and also come up with an equilibrium constant describing this reaction. In this case, one of the water molecules will go ahead and pluck a proton off the other water molecule, now forming the hydroxide anion and the hydronium cation. The thing to keep in mind here is that the K value is, as always, products over reactants, and then the actual value of this equilibrium constant is 10 to the minus 14. If you didn't know this number already, this is one you need to have memorized by test day. But it makes a lot of qualitative sense. Water is super stable, and that's reflected in the very small magnitude of the equilibrium constant describing this reaction. This reaction is significant because we have water itself being both acid and base in the same reaction. Recall that the hydronium cation is literally the definition of acidity. So if an acid has a K value greater than 1, that means that that acid is more reactive than the hydronium cation, and that's actually where we get the term strong acid. If a molecule's K value is less than 1, that means it's less reactive than the hydronium cation, and that's what makes for weak acids. But remember, the autoionization reaction is significant because here we see water itself acting as an acid. Well, if a molecule's K value is less than 10 to the minus 14, that means that molecule is actually less acidic than water. We don't normally think about water as being an acid. We usually think about it as being inert. So you can generally consider any molecule whose K value is less than 10 to the minus 14 to be not really an acid at all. This is an important point. It means that there are 3 ways to categorize a molecule when it comes to acids. You can have strong acids or weak acids, but the third option is a molecule could just not even really be an acid at all. So while we're at it, go ahead and pencil in on this hierarchy where you would expect to find hydrofluoric acid and hydrochloric acid. Following these definitions, HCl is clearly a strong acid, where HF is definitely in that weak acid zone. Let's consider bases as well. Bases are important for any discussion of acids because when an acid gives up its proton, that molecule becomes a base. It becomes, at that point, a proton acceptor. Since both HCl and hydrofluoric acid are going to react in your body and turn into conjugate bases, we want to think about the effect of those bases as well. In the same way that H3O+ was literally the definition of acidity in solution, OH- is literally the definition of basicity. So what I'd like you to do, we have OH reacting with water on screen. Think about the products of this reaction and also generate a base constant, Kb, that would describe the reaction between OH and water. Here, hydroxide is going to attack one of the protons on water. Of course, that turns hydroxide into water, and water, having lost a proton, becomes hydroxide. So, as with the hydronium cation, we see another special case. Again, the base constant for this is products over reactants, where they're the same thing, and so this reduces down to 1. And as we saw for acids, if a molecule has a Kb that is greater than 1, that means that molecule is more reactive than hydroxide, which is the literal definition of basicity in solution. That's where we get strong bases from mathematically. At the same time, if a molecule's Kb is less than 1, that puts it into this weak base realm. But remember from the last page, water in the autoionization reaction is not just acting like an acid. The other molecule of water is itself acting like a base. And that means that if a molecule's Kb is less than 10 to the minus 14th, that molecule is less reactive than water. Again, we don't really think of water as very much of a base, so if a molecule is less reactive as a base than water, that molecule is really not even a base at all. This next prompt reveals a really important clue about why hydrofluoric acid is so dangerous. It says that when it comes to hydrofluoric acid, it's not just the protons that you have to watch out for, but actually the conjugate base, the fluoride anion itself, is also reactive and can also cause you physiological harm. By contrast, for the strong acid HCl, you got to worry about those protons, but the chloride anion is super safe. Let's use mathematics to figure out why this is. The relationship that relates the reactivities of a conjugate acid and its conjugate base is Ka times Kb equals Kw. We know the Ka for hydrofluoric acid, so use this relationship to compute the Kb for its conjugate base, for F minus. With a little bit of calculation, we see that the Kb for fluoride anion is 10 to the minus 9th. Notice that because HF's Ka is a little bigger, that means that the Kb for the conjugate base is a little bit smaller. But if we think about our hierarchy of acidity and basicity, this means that the fluoride anion itself is safely inside of that weak base zone. Therefore, when you get splashed with hydrofluoric acid, not only do you have to watch out for that hydronium cation that's going to be formed, but the fluoride anion itself is a weak base that's now circulating throughout your system. Nasty stuff. Let's play that same game for hydrochloric acid. We again know that the Ka for hydrochloric acid is 10 to the 6th. Using that information, compute the Kb for the conjugate base, Cl minus. Using a little bit of algebra, we find that that Kb value is 10 to the minus 20 for the chloride anion. Here, notice that because the Ka value for HCl is huge, that means that the Kb value for its conjugate base is infinitesimally tiny. This is way, way less reactive than water. And in fact, if we look at our hierarchy, HCl may have been a strong acid, but its quote-unquote conjugate base, Cl minus, actually isn't even a base at all. Or technically, a scientist would say that Cl minus is less basic than water. The point is that for HCl, it may be a strong acid, but it's only the acid that you've got to worry about. Once HCl gives up that proton, the other product, Cl minus, is pretty much inert, and you don't have to worry about it physiologically. So a quick recap. Hydrofluoric acid, despite being a weak acid, is actually more dangerous than hydrochloric acid for a number of reasons. 1. Hydrofluoric acid dissociates slowly over time, so it's harder to control the damage that it's causing. 2. Hydrofluoric acid dissociates into dangerous protons, just like hydrochloric acid, but hydrofluoric acid also contributes the fluoride anion, which is itself a base that can attack your body. But probably the most damaging aspect of hydrofluoric acid is the fact that hydrofluoric acid can penetrate into your skin, enter your circulatory system, and attack your vital organs. And in fact, it's actually hydrofluoric acid's status as a weak acid that allows it to do that. Let's find out why in this final prompt. So let me hand this question off to you. If I have HCl and hydrofluoric acid, the fact that HCl is a strong acid means it's going to immediately dissociate into protons and chloride anions. Hydrofluoric acid, being a weak acid, will hold it together. Why does this explain why HCl only burns the outside of your body, your skin, whereas hydrofluoric acid can penetrate through tissues and enter your circulatory system? Recall that charged molecules can't cross lipid bilayers. So if you were to splash some HCl on your skin, the protons would corrode the outside of your body, but they wouldn't be able to penetrate any deeper than that. By contrast, hydrofluoric acid is uncharged and remains together in solution. So, for that reason, it can easily cross your skin and then move from your skin down to your muscles and pass from your muscles into your circulatory system. Eventually, that HF will pop apart into corrosive protons and fluoride anions, but the point is, it can make it much further into your body before it splits into those corrosive products. When most students think about acid-base chemistry, they think about strong acids and bases and weak acids and bases. The big revelation in this lesson is that there's a third category. An acid or base can also be less reactive than water, or basically inert. I hope that helps clarify some of the questions that you have about this very challenging but very high yield topic.